denote it as E. Then we need to know the orbital elements. The next orbital element, which is the semi-major axis, which is denoted by A. Then the farthest point of the satellite from the Earth, which we call it as apogee. Then the closest point of the satellite that approaches to the Earth, which we call it as perigee. So these are the fundamental orbital elements that we need to consider. Second, on the secondary side, we need to see the line of apsides. So the line of apsides is the lines that join the perigee and apogee to the center of the Earth. So the perigee point and the apogee point will be joining each other to the center of the Earth. So that point we call as the line of apsides. So next orbital element is the nodes. It could be either your ascending node or your descending nodes. So ascending nodes are the points where the orbiter crosses the equatorial plane, meaning that running from south to north. So you could have seen the globe. Okay, you can see all being denoted in a single, but I'll show you the globe. Then you'll be able to understand. So here, the line of apsides. Then we have the ascending nodes and the descending nodes. So the ascending nodes are the points where on this globe, the points running from south to north. So this bottom from here to the top north. So that we call as the ascending nodes. So descending nodes is the next, which is the point where orbit crosses the equatorial plane, moving from north to south. Okay, in reverse to that. From top to bottom, when it proceeds and the point crosses, that we call as descending, and from south to north, when it crosses, it is called as ascending. So ascending nodes and descending nodes, line of apsides, perigee, apogee, semi-major axis, and eccentricity. All these are the basic orbital elements that defines the Earth orbiting with the satellites. So these are being represented in a single pictorial diagram. The apogee, which is the farthest point, which is revolving, you can see that. So apogee is denoted here. So at the center is the Earth and the satellite being rotating. So these dots are your satellites. These are your points. The farthest point is the apogee. Closest point is the perigee, which is represented here. As I'm dragging my mouse, you can see able to see the orbiting of the satellite around the Earth. The farthest and the closest points. Apogee, perigee. Then, so say this is revolving here. It's in the fashion of a circular. So this is the node. Okay. Then we have the ascending node. You can see here. This is revolving in this pattern. Yes. This is your ascending node. So moving from south to north. Okay, from south to north. And this is your descending node, moving from north to south. This side. Then this is your equatorial plane. This is revolving around the orbit. So then this is your line of apsides, which connects the apogee point and the perigee point to the center of the Earth. So this is your line of apsides. Then the line of nodes is a connecting point. Okay. So these are your orbital elements. So the line of nodes is the line joining the ascending and descending nodes. to the center of the Earth. As you have seen in the diagram, the ascending node and descending nodes are being connected through the center of the Earth, which we call as line of nodes. Then we have the right inclination and the right ascension of the ascending node. So this right ascension of the ascending node is the angle being measured between line connecting the center of the Earth with the ascending node. And there is another line that is being connected from the center of the Earth to the initial space. You can see thus the line connecting to the initial space. Then the argument of perigee, the angle between the ascending node to the perigee. So this is omega, the angle between the ascending node. So here is the ascending node, the angle with that with respect to the perigee, which we call it as argument of perigee, denoted by omega. So next topic is the orbital perturbations. So in order to get the ideal conditions of the orbital perturbations, we need to consider the orbit as an ellipsoid, uh, where the properties of them are constant with respect to time. So in practice, the satellite and the Earth respond to many other influential factors, such as a gravitational field. In terms of Earth, since we are present on the Earth, we are being bound to stay there, and with that we need to find the other's gravitational force, like the gravitational force of the sun, the gravitational field of the moon, the radiating pressure of the solar system. So all these are to be considered when we want to analyze each and every planets or the whole entire solar system. So for the satellites that are being deployed in the low Earth orbiting, we'll see that what is the low Earth orbiting, how it is being formed in the subsequent slides. So for low Earth orbiting or the LEO satellites, the atmospheric drag is an important factor, such that the gravitational pull can be averted. So all these forces, the gravitational field of the Earth, gravitational force of the Sun, the Moon, and the solar radiation pressure, causes the true orbit to be different from the ellipse. So the perturbations are assumed to cause orbital elements to vary with respect to time. So we'll see that due to those effects, what happens. So due to the effects, the longitudinal changes, the longitudinal changes because due to the effect of the Earth's obliqueness. Because the Earth is neither a perfect sphere nor a perfect ellipse. So the Earth is flattened at poles. You can see that we have a North Pole and South Pole. Okay, so at the poles, the Earth's surface is always flattened. So the equatorial diameter, which is about 20 kilometer, is present at an average polar diameter. So this equatorial radius is not a constant, where at equatorial it is around 100 meters around the equator. So at the poles, the diameter is flattened, so it is about 20 kilometer. Whereas at the equator, it is 100 meter. So the Earth is not a perfect sphere nor a perfect ellipse. So due to the Earth's obliqueness, the area of coverage of the satellite is to be considered. So this leads to the longitudinal changes, which is a main effect of the Earth's obliteness. So there are some regions on the Earth where the gravitational attraction is very much higher. So those regions are called as mascons, so which are referred to as regions of mass concentration. You could see in some places in United States there is a very high gravitational force. So that type of regions are identified as mascons. So according to that, we need to adjust our orbiting principle. And that's what we call as orbital perturbations. So these non-regular features of the Earth leads to non-uniform gravitational field around the Earth. So this will force an orbiting satellite to vary with its position. So at one place, the Earth is flattened, and one place the Earth is radius is not a constant, and some places higher gravitational force is available. So during this process, if the satellite moves in, or its satellite is orbiting the Earth, due to this higher gravitational force, the satellite may get attracted towards the Earth, and it may fall down. And when it moves towards the poles, it may not get proper area of coverage. And at the equator, it will have lesser gravitational force. So, considering all these things, we have to design an appropriate satellite. So, you can see that the equatorial diameter, you can see, is around 12,756 kilometer equatorial diameter, which is measured at this place. So, from here to here, you can see the globe. So, the equatorial, you can see the diagram. Kindly be awaited. How are you, Ra? Fine, Ra. Uh, Let us resume back. So you can see the equatorial diameter is 12,12756 kilometer, whereas the polar diameter from the pictorial representation it is 12714 kilometer. So all these things has to be considered while designing an satellite to be placed in orbit or in space. So such a difference is a big task for the researchers or the scientists to put an geographical mapping in order to sense and in order to continuously monitor the exact places. Because sometimes when the satellite is orbiting, the Earth is also orbiting its own axis, it is in motion. So at some point of view, the satellite may get attracted or may get reflected or may get malfunction. So the placing of the satellite should be done in accordance to that, considering all this. If this gravitational force is present or if this gravitational force is coming into it, how the satellite has to react. Okay, so those are the basics. So next is a geo satellite. It is a weightless when it is in orbit. So the smallest force on satellite will cause it to accelerate and then drift away from its nominal location. There will be generally an additional force towards near, near the equatorial bulge, either in eastward or westward direction along the orbital plane. Okay. So the same, the obliqueness does all this work at the equatorial force or at the equatorial bulge. There would be a drift towards eastward direction or westward direction along the orbital path plane due to the obliqueness. So all this has been considered and they are being analyzed. They have found out that due to the position of mascons and equatorial bulges, due to the position of the mascons and the equatorial bulges, there could be four equilibrium points in the geostationary orbits. One could be the two stable points, another could be the two unstable points. So, what are those points where the mascons or the equatorial bulges occur and leads to stable and unstable positioning is that 75-degree east and 252-degree east. And the unstable points are that 162-degree east and 348-degree east. So, when the satellite is being launched, geo satellite, it should it should be in a position such that it doesn't move in the 162-degree east, and it when it moves on to 162-degree east and 340-degree east, it should have an appropriate system to make it stable. Okay, and the very much a stability point is your 75-degree east and your 252-degree east. So there you can make always with respect to Earth, you can place your satellite pointing towards that. So the satellite at an unstable the satellite at an unstable orbital location is at top of a gravity hill. So what will happen is that if a small force is given due to the other celestial bodies or asteroids or other satellites, if they give a small drift, if a small force is given due to that, it will drift down the gravity slope and it will fall into the gravity well and finally it will stay there. If a satellite is perturbed slightly from one of the stable points, it will tend to drift back the stable point without any thruster firing is required. And if the satellite is perturbed slightly from one of the unstable points, it will immediately begin to accelerate its drift towards the center stable point, and once it reaches this point, it will oscillate in longitudinal position about that point until it stabilizes to that point. Till the stabilization occurs, it will move if there is any external forces being given. So these stable points are called as the stable points that occur due to this perturbations is called as the graveyard geosynchronous orbit locations, or simply geosynchronous orbit locations. Geosynchronous orbit locations. So whenever we place a satellite in the space, it should be a stable point. So if it reaches that point, then that location is called as geosynchronous orbit location. So any doubts or any queries till this? If there are any queries, you can type in chat box. Then we'll proceed on to the next topic, which is inclination. I'll give you some 4 or 5 minutes of time. Any queries? Kindly type in chat box. Since I couldn't find any queries in chat box, we'll proceed on to a demonstration on how the shape of the Earth is.
What is the shape of the Earth? Before we get started, please get out your packets, open to page number 1, and we will be filling in the top section of this page as the video progresses. Hello and welcome. In this episode, we are going to attempt to answer the question, what is the shape of the Earth? Before we get started, please get out your packets, open to page number 1, and we will be filling in the top section of this page as the video progresses. Let's begin. So, what exactly is the shape of the Earth? Well, you might be thinking to yourself, duh, the Earth is round. That's obvious, everybody knows that. However, if you look back at history, there's a long list of stories of people's terrible fears of falling off the edge of the Earth. One of the more notable stories involves explorer Christopher Columbus, who, when he set sail for the New World in 1492, had fears that he and his crew would meet a terrible end falling off the edge of a flat Earth. Interestingly, Columbus would later be credited with the discovery of determining that the Earth is in fact round by not falling off the edge of the Earth. But that's not exactly true. In fact, we've known that the Earth is round for thousands of years. In fact, this Greek philosopher named Pythagoras, who was also a mathematician, made the observation more than 2,500 years ago that the Earth has to be round, simply based on logic. But that's not enough. How exactly do we know the true shape of the Earth? In this discussion, we're going to take a look at 4 pieces of evidence, or 4 proofs, that will hopefully convince you of the true shape of our planet. Let's take a look at proof number 1. Now, proof number 1 involves the Moon, our closest neighbor in the solar system, seen here at its various phases, which can be visible from Earth throughout the month. People have been observing the moon for thousands of years, and they have noticed that the lit up portion of the moon has different amounts visible at different times, and this can be seen in this diagram. Now, the only way that these strange shapes of the illuminated sides, the crescents, the gibbous, the first quarter and last quarter, the only way these shapes would be visible is if, in fact, the moon is round. And yes, it is a big giant sphere orbiting the Earth. Now, early astronomer Aristotle, who lived more than 1700 years ago, noted this, and he went a step further. He observed the moon during lunar eclipses, and what Aristotle noted was that during a lunar eclipse, the Earth's shadow is cast on the moon, and the Earth casts not a straight shadow, but a rounded shadow. Aristotle deduced that the only possible shape that can always cast a rounded shadow is a sphere. And from that moment, we had our first piece of concrete evidence of a spherical or round Earth. Let's go to our handout. Proof number 1 is that the Earth casts a rounded shadow on the moon during a lunar eclipse. You can pause here and fill in that portion of your handout. Let's move on.
Hi, I'm Ankit Bharia. As a travel filmmaker, I have had the great pleasure of visiting some of the most beautiful, natural, hidden.
We need some more evidence, because I'm certainly not convinced yet. So here comes proof number 2. Imagine going down to the ocean and looking out in the distance at a vast sea ahead of you. Off in the distance, you will see the horizon. The horizon is the point where the sea meets the land, shown here by a horizontal black line. Now imagine your friend is taking his new ship out for a nice sail on the high seas. Now, of course, as your friend gets further away, the ship is going to appear smaller and smaller and smaller. That is our rule of apparent diameter. As something gets more distant, it appears smaller. Easy. But if you watch carefully, as your friend and his ship get further and further away, they will actually appear to sink over the horizon. Now, one of 2 things could be true. First, he could actually be sinking, which would be a terrible shame. But the more likely explanation involves the shape of the planet that he is sailing upon. If you look here, the dotted line is showing a line of sight from you, the observer. Now, as your friend sails away, you'll see most of their boat for quite a while. But as they go over the horizon, the ship is going to appear to sink. In reality, it's not sinking, it's simply traveling along the curved surface of our planet. You can see that in this photograph here. This is a large steam tanker, and all that's visible from this distance is the top of the mast. The main part of the ship is around the curve of the Earth and not visible from where we are. Even more impressive is this photograph of the city of Toronto in Canada. When you look at it, only the tip tops of the tallest buildings are visible. That doesn't mean the whole city is sinking. What it means is that it is so distant that it is seen only partially due to the curved surface of the Earth. And that's evidence number 2. So go to your handouts, and in proof number 2, we're going to write what we call the sinking ship theory. Ships appear to sink as they pass over the curved surface of the Earth. Pause here and fill that in. So let's move on to proof number 3. This is a really interesting one. Let's take a look at an Earth. Here's the Earth. And let's imagine slicing the Earth in half so that we could look inside it. Now, don't worry about all these layers. We'll be learning about the interior of the Earth later in the year. But for the moment, let's imagine an individual observer standing on the surface of the Earth, let's say right over there. Now, this person could weigh themselves on a scale to determine how much they weigh. How much you weigh is in part a result of the pull of gravity. The more gravity, the more you weigh. So, what impacts how much gravity there is? Well, in part, it is the distance between you and the object's center of gravity. This is to say that the closer you are to the center, the more you will weigh. The further away you are, the less you will weigh. Keep that in mind. Now, let's say we had an oddly shaped planet, shaped kind of like a big egg, almost. Our observer on the top is actually a little bit closer to the center of the Earth when he's at this top portion of the planet. That's going to cause him to weigh more. If he moves over here, he's a little further from the center of the planet, causing him to weigh less. So if the Earth were any shape other than a sphere, our weights would vary dramatically as we went to different places on the Earth. But the fact is, if you take the Earth and you put individuals at any point you want on the planet, and you open up the Earth and you weigh these people, they're going to weigh just about the same thing everywhere. And what we can conclude from that is that everywhere on the Earth is the same distance from the center. And if that is true, the Earth must be a sphere. Let's go to our handout. This will be proof number 3. The pull of gravity is just about equal from any point on the Earth's surface, proving that the Earth is spherical. One more to go. Proof number 4. And this one is really easy. Unfortunately, it's restricted to modern times. Proof number 4 involves photographs. This photograph of the Earth right here was taken way back in 1972 by the crew of the Apollo 17 mission. As they flew their way to the moon, they would eventually land there and walk on the moon, but on the way, they turned their capsule in such a way that they could photograph the Earth. And what's so special about this photograph is that it was the first time we've ever captured the full disk of the Earth. That's because this photograph was taken while the sun was behind the astronauts, and so you could see the entire illuminated side of the Earth. Now, to me, this is pretty convincing evidence of a spherical planet. We can actually now go to space and see the Earth and actually directly observe its shape. But again, some might argue, based on this picture, oh, maybe the Earth is shaped like a frisbee or a disk, and it's not really a sphere. Well, we've got evidence to answer that question as well. A little bit later on in 1990, the Galileo spacecraft turned around, faced the Earth, and took this time-lapse video, one of the most beautiful videos of the rotating planet ever taken. And this becomes pretty much undisputed evidence that the Earth is in fact a sphere. And so that's going to be our proof number 4. we can now actually travel to space and take photos and videos of the Earth directly observing its true shape. And so those are our four major pieces of evidence supporting a round Earth. Now, of course, I could go on and on. We actually have dozens of proofs, but these are the four that we're going to focus on in our class. Just a quick review. The four proofs for a round Earth include the shadow during a lunar eclipse is round, so the Earth must be round. The sinking ship observation, where ships appear to sink as they pass over the horizon. That proves that the Earth is round. The fact that no matter where you go on the planet, there's an equal amount of gravity. That proves the Earth must be round. And then, most convincing of all, the fact that we can go and actually directly observe the Earth from space. That proves that the Earth is round. Thank you. Have a good night.
Yes, Mr. Reddy Pranith. Any queries? You have raised your hand. If you're having any queries, kindly type in chat box. Yes, Pranith, you can type in chat box. Are there any queries for this session? Since there are no queries, the attendance link for today's session is being provided in the chat box. Link will be active till 12 noon only. The students, those who fill this Google form only will be given attendance.